Hi, my name is Norah Zhou. I am a part of Fuse Breakers, and today in this video we will be going over how to use a multimeter and how to build a simple circuit. So in this first part, we will be learning how to set up and use our multimeter. A multimeter is a measuring instrument that can basically measure voltage, current, and resistance. So if you need to set this up, we have these black and red knobs with these pointy ends that we use to measure the voltage. And to set it up, we will put this black lead into the common port, and this red one into the voltage port. And basically you can turn it on to voltage direct current, but if your multimeter is a little different, it will look just like that. Okay, so now we will be testing our batteries, just to know if they're good or bad. So on this D battery, we should expect 1.5 volts. So the red wires is positive and the black is usually negative. And if you align the positive with the positive and the negative with the negative, you can see on our multimeter right here that we have 1.555 volts. I'll write this down. And that means we have a good battery. On this AA battery, we should expect 1.5 volts. And if we line the positive with the positive and the negative with the negative, we get 1.146. And that is below 1.5 volts, which means this is a bad battery. Okay. And then lastly, we have this AAA battery, from which we can expect 1.5 volts. Once again, line the positive with the positive, the negative with the negative. And we see that we have 1.537. And that is above 1.5 volts. And so this is a good battery. Next up, we will just measure the voltage of our 4 AA battery pack right here. It is cumulative, which means each battery voltage adds up. And since we have 4 AA and they individually have 1.5 volts, we should get around 6 volts. So if we just match them up, you can see in our screen that we have 6.40 volts, and that is correct. A little bit over 6 volts, but that is okay. Next up, we will be taking a look at resistors. Our goal is to verify if the resistor is within plus or minus tolerance, and I will explain what that means a little later. Okay, take a look at this first resistor, if it will focus correctly. It's a little far, but if you look at this, you can just faintly see a yellow band, a purple band, and this is a brown band, believe it or not, and the gold band. If we look at this chart right here, you can see that a yellow band is 4, purple is a 7, and a brown band is a 10. I'll explain how to calculate the resistance. So you take this first one, 4, with the 7, and that becomes 47. And then we multiply it by the multiplier, which is 10 in this case, to get 470. Just like it has it up here. So basically, our expected resistance is 470 ohms. And I think we use the omega Greek letter for this. And the percentage, plus or minus, would be 5% because we have this gold band. So it would be plus or minus 5%. If we take a look at this next one, we can see red, black, red. So if we take a look at the chart, we can see 2, 0, and the multiplier is 100. So that would be 20 times 100. So 20, which is 2,000 ohms. And since it is a gold band right here, it is a plus or minus 5%. Okay, lastly we have this resistor. You can see brown, black, and red. And so if we take a look at the chart, you can see 1, 0, and the multiplier is 100. That's 10 times 100, which is 1,000 ohms. Once again, it is plus or minus 5% resistance. Okay, now we will be measuring these resistors, starting with the first one. You can, a little awkward, but we can see it's 0.463 kilo ohms, and that is roughly, I don't know, the glare is pretty bad. But it says 0.464 kilo ohms, and that is a roughly 464 ohms, and that is within our plus and minus range of 470. And so it is okay. That's a little rough there, sorry. Okay, next we are moving on. Ooh, it turned off. Next we are moving on to our second resistor. And if we measure that, we get 1.95, and that is roughly 1,950, which is within our plus minus 5% range, I believe. And our last one, if there are these paper strips on them, just go ahead and take them off. There you go. Okay. And once again, we just, excuse me. You just measure it right there. And you get around like the around 0.995, and that is roughly 995 ohms, and that is within our range. So all of these resistors are okay. There you go. Okay, next we will be learning how to make a simple LED circuit. Make sure you are wearing safety glasses while doing this. Okay, first you need a 4 AA battery pack, our 2K or 2000 ohm resistor that we just used, an LED light like this, and 2 alligator clips. You can use 3 if you want, but 2 is all you need. Okay, so what we're gonna first do, you can skip this following step. if your battery pack doesn't look like this, but if it does and it's connected right here, it is easier to use one of these in order to connect your alligator clips. So just connect the black wire to black and red to red, right there. These will fall out easily, so just make sure that they're connected pretty well. Okay. Next, excuse me. Okay, we're gonna connect the white alligator clip to the positive side and the black to the negative side. Make sure that they stay in. Okay. We're gonna take the resistor, connect it with the black, and take the longer side of this LED, which is this side right here, and connect that to the white alligator clip. Essentially, it should light up just like that. Okay. Next, we're gonna just look at the question right here. It essentially is asking you what would happen if you used lesser resistant resistors. So if we just take the two that we just used or looked at in the last step and we compare it to this one, let's go ahead and do that. Make sure they're connected, all of them. Take a look at that. Okay, this is the highest resistance. This is 1000 ohm. That looks a little brighter. It might not register fully on the camera, but do your best. And then this is the lowest resistance. As you can probably or maybe see, it is significantly brighter. Okay, I'm gonna switch between the 2000 and the 470 ohm. That is 2000. And then this is the 470. You can definitely see that it's brighter. Okay, so let's read the question. What happens to the LED as resistance decreases? So basically, the LED gets brighter. Essentially, what happens when the resistance decreases is more of that power is going towards the LED and allows it to become brighter. Okay, and a circuit is basically a series. It's like, which you can read right here. The components are connected along a single path. In a series circuit, the current through each of the components is the same, but you can change the current by changing resistance, which is basically the resistor. That just helps the components from firing, because if there's too much power, then it will basically fire. Also, safety glasses are very important. If we connected the LED to the battery without a resistor, it would blow up. So safety first, always. The next step, we will calculate the current in the circuit using our 3 resistor values. So we basically take the voltage, which is 6, divide it by the resistor value, 2000, and then we have to actually multiply by 1000 because there are 1000 milliamps in amps. So 6 divided by 2000 times 1000, and then we get 3 milliamps. You can do the same. 6 divided by 1000 times 1000 equals 6 milliamps, and 6 divided by 470 times 1000, and you get roughly 12.7 milliamps. And as you can see, this makes sense because if the resistor value is lower, then more current is getting to the circuit. And that's basically how you use Ohm's law to calculate the current.
Welcome back to how to use a multimeter and build a simple circuit. My name is Zhou, and I'm part of Fuse Breakers. So where we left off is on step number 7. We have not done this yet. Now, step number 7 says that we have to measure current in the circuit using a multimeter with no LED, and then compare your calculations above with the measurements below. As shown, there's a diagram right here, and a chart with the resistor value and the current measured in the circuit. Also below is the question of the day. Are the values of number 5 and number 6 the same? And if not, could you explain the difference? Now we're going to cover how to do the circuit. So the materials that you need, as shown, is a multimeter that is set to amps. That symbol. And then you have to also ensure that the black wire remains on comm, and the red wire on milliamps. You will need to use a battery pack, as well as some wires and a resistor. So let's start. We're gonna put this here, and multimeter is gonna start measuring it. As seen right here is roughly 13, so let's put this down. That'll be for resistor number 1. Alright, so we hook up the resistor to the circuit. Let's start measuring it. As usual, we put these clips in, like so. Ooh, this is hard. As usual, we have to set our multimeter back up and make connections. It might be a bit difficult to do this on camera, but we'll try our best. Oh, it. So the general consensus here is that it's 3.10, which is significantly lower. $300. This is a 300 ohm resistor with 3.10 milliamps that's drawn. Or at least I believe that it said that. Alright. Now let's do the last resistor. This one's a brown. It has a black and a red. And plus a gold. Let's look at our chart again. This one's the easy one. It's 1, 0, and 100. So, I believe that this one is 100 ohms, around so. Let's hook it up to the circuit. Again, we take out the clips. This one's off camera, yeah, this one's off camera. Let's hook up the clips right here. And once again, let's attach our leads to the multimeter. Let's see what it finds. Let's see. Ooh, this one's really low. That's 0.13. Oh wow. You can see that it gets progressively lower as the resistor values go down. Okay, so you guys have probably seen that this setup is very different from the one that we used before. It is because this thing, shortly after I finished filming the last segment, it started smoking. Now I immediately unplugged it and brought it outside and then waited for it to cool down. But by then it was so hot that the plastic had melted and it was unusable. And even if I use it again, it would be probably pretty dangerous, so don't try to use damaged electronics in a circuit. It happened because of a short. Always check for electrical shorts in your circuits. And if a component feels too hot, remove it immediately and let it cool down. So what I'm using today for number 8 is snap circuits. I had these snap circuits for a long time. They were just sitting around. And if you have any in a house, these are pretty useful too. So for activity number 8, we're gonna insert a single pole, single throw, toggle switch into your circuit anywhere you like. This is a simple on-off switch, and we're gonna use this LED for the first test. All right. So before we get started on this demonstration, we're gonna talk about how I wired this thing. So as you can see, this is obviously a very different system than what I've used in the last step, but it follows the same electrical principles, which is positive, it goes through, which goes through this little bar here, and then it goes up the screen wire to this switch. Alright, then it follows this red wire to this little LED board right here. Then it follows this white here, back and back again. Alright. So it follows the same principles as the regular circuits. Okay. So we have our single pole, single throw switch ready to go here. Let's insert our batteries. Plus to minus and minus to plus. There we go. Now, voila. Hopefully you guys can see this little LED right here light up. Alright. And yes, it should turn on and off with the switch. Off, on, off, on. Alright. Just safety precautions. Okay. So we're gonna detach these and put them to our motor. So the motor can handle up to 18 volts, so a resistor is not needed or wanted. And we're gonna test the motor. So obviously I'm using the one supplied with the snap circuits kit. Your guys' kits should have like one of these little can motors here that are used in many applications. Follow the same principle. You just put, these little clips in those little copper tabs right here, and that'll power it. be sure to follow the positive and the negative. To make this a bit more visible, I'm gonna put this in this nifty little fan on top. It just slides in like this on top of the motor blades. Oops. Yeah, this one's a bit tricky to get on camera. Alright. You guys can see that, right? Alright, let's go. Oops. As I said, this is a very tricky thing to put on. Alright. So, let's go. Oh, I have to put in these power things. Hold up. Silly me. And it's on and running. So we can turn this on and off. On, off. Hopefully that should cover number 8. We're using a simple circuit, which is basically the battery, the power. It goes to a switch. It goes to your LED or motor. And it goes back. So the motor, as seen here, can spin in one direction. Excuse me. Okay, so for number 9, this is pretty straightforward. We're going to use electronic symbols. We have to see the component chart. We have to draw a circuit that includes a battery, a SPST switch, a resistor, and an LED. Now, for the sake of time, I'm not going to use the electronic symbols and instead go straight to drawing the components. So we're going to first have a battery pack. So I'm just going to label this battery pack, as seen here. You have a positive and a negative. Yeah, I should make that. Let me. Negative. Okay. Now we're gonna go to a single pole, single switch, SPST switch. So let me draw this right here. Okay, we're gonna connect this to a positive. So this is the receiving end of it. And let's draw LED right here, like a good big LED. Okay, and we're gonna go here. LEDs have 2. So this one is the positive receiver. Let's start with the negative side. So we have a resistor midway, like so. It goes here, it goes to the resistor, and back. So that's number 9. Hopefully I shouldn't find that step too hard. It just takes a little bit of understanding and knowing how to draw a little bit. It's not too difficult. Alright, on to step number 10. Okay, so we're going to remove our single pole, single throw toggle switch and replace it with a double pole, double throw knife switch. So we're going to look at the picture carefully to clip everything together. So as shown, everything is clipped together corresponding to color. So red and black and white and the yellow. So all of it is clipped together right now, everything's set up. A few notes is that could you make the switch make the motor turn in both directions? And then we also have to look carefully at the wiring of the dpdt knife switch. It's from top to bottom, and if you look carefully, every piece of metal on the switch is a conductor. This is the battery positive and negative, and both of these are connected to the motor right here. And here's a diagram of what will happen when a double pole, double throw switch is thrown. Alright, let's get down to do this. So, yeah, this is, the fan keeps falling off. Just wanted to demonstrate. Alright, as you can see, it's, oh wow. Yeah, so this motor has enough to generate lift on this. Let's throw it the opposite direction. Yep, alright. Let's do this. As you can see, it's spinning the opposite direction. And like so. Like so. So... oops. Yeah, these things are really fun to play with if you ever have one of these. It's just the fan blade's just for this demonstration, make it visible, right? So it's this and the other side, right? So gotta apply the power carefully next time. Make sure it doesn't fly off again. Oops. Yep. Okay, as you can see, you can spin both directions. And on your pufferfish control box, you would use a dpdt toggle switch. It will be a rocker switch rather than a knife switch. So we're gonna write down the difference between a single pole, single throw, and a double pole, double throw switch. So a single pole, single toggle switch, like so, it will make it go in one direction. But a double throw will reverse the polarity, which can make a motor turn both ways. So that is it for number 10. For your wiring, you just have to wire your battery pack to the positive right here, and then the negative back via this bar on my example, and these are to the motors. So that is it for number 10. Using a diagram, you can figure out how to hook this up pretty well. And if your motor's not working, be sure to check that everything's working properly. So, yep, this is number 10. Now we're gonna go on to number 11. Okay, so, yeah, we covered number 10 and number 11. Now we're gonna move on to number 12. Now, in number 12, we're gonna do what fuse breakers got its name from. We're gonna break a fuse. Stay tuned. Alright guys, so we're on step number 12. We're gonna break a fuse. Now, before we start breaking a fuse, we gotta have our safety glasses on. Because safety is our number one priority. Let's look carefully at our 3 amp fuse. It has an S-shaped wire that will be broken when it's overloaded. So we're gonna connect the positive of this D-cell battery to one end and the negative to another. Now it will break once we do so. So we're gonna look at this for one last time, and then we're gonna connect it and break it. This is also where fuse breakers got its name from. Many years ago, we broke a fuse and we bonded together as a team afterwards. It's a really good time that we all had. Yeah, so without further ado, let's start breaking the fuse. So we're gonna, slide this positive alligator clip on here for the last time. Positive is live. Now the negative one. Alright guys, alright fuse. It's gonna be a good journey for y'all, and it's gonna finally be broken. The S-shaped thing, the S-shaped wire is gonna be broken. Alright. It might take a while. Alright guys, so you might not see it, but a little bit of the inside wire broke, so yeah, we call this a success. We broke a fuse. Yeah, just like fuse breaker's namesake. Alright, that concludes part number 2, and we're gonna do a simple recap. Alright, so we have finished breaking the fuse. Now we're gonna review the important concepts that we learned in this unit. So the voltage is the difference in charge between 2 points, which is measured in volts, that's a V. A current is the rate at which the charge is flowing in the circuit, measured in amps or milliamps. 1 amp equals 1000 milliamps, or 1A, or 1000 milliamps, which is right here. Resistance, which is resistance to electron flow, measured in ohms, R. 1000 ohms equals 1 kilo ohm. That's 1 k ohm or 1 k omega. To build a simple circuit, you need at a minimum a voltage, which is a battery or a wall socket conductor, a conductive path, which is a wire, and a load, which is lipo, motor, screen, etc. So this concludes this series on how to use a multimeter in building simple circuits. I hope you enjoyed these 2 videos, and if you did, please consider leaving a thumbs up, smash the like button, and be sure to subscribe to Fuse Breakers for future videos to come. Thank you and have a good day, everyone. Cheers.